Welcome to this explainer. Today we're unpacking a really fascinating engineering pivot behind a project called the AquaGuard Sentinel. We're going to look at how engineering student Sierra Tate transformed an affordable, automatic water leak detection and shutoff system for RDP housing, which is a government-subsidized housing program, from just a theoretical concept into a truly reliable, real-world hardware solution. As you'll see, we're going to dive into exactly how rigorous testing forced a complete rethink of the system's core safety design.
So let's dive right into the foundational challenge of the AquaGuard Sentinel. How do you build a fail-proof smart home alert system on a really tight budget? Because when you're designing for budget-constrained housing, literally every single component cost matters. You absolutely need a way to alert homeowners of water leaks to prevent devastating property damage, but you just can't break the bank with expensive enterprise-grade hardware. It has to be accessible, it has to be cheap, and above all else, it has to actually work when disaster strikes. Here's our roadmap for today. First, objective, remote leak alerts. Second, bench testing the SIM800L. Third, root causes of module failure. Fourth, evaluating reliable alternative options. And finally, the final system architecture. All right, let's jump straight into Section 1, Objective, Remote Leak Alerts. The initial expectation for this project was beautifully simple, right? The system just needed a low-cost method to ping the homeowner the exact second a leak was detected. Now, because Wi-Fi isn't a guarantee in RDP housing, the team was led straight to the ultra-cheap SIM800L module. This is a basic 2G GSM module that costs a fraction of modern LTE boards. On paper, it looks like the absolute perfect budget solution to just shoot off a quick text message alert over the cellular network. Moving right along to Section 2, bench testing the SIM800L. Now take a close look at the physical power setup here. You can't just snap these parts together like Legos. The main controller being used is an ESP32 dev board, but the team deliberately bypassed the ESP32's own onboard power pins. Why? Well, because a GSM module like the SIM800L has massive transmit bursts. When it tries to talk to a cell tower, it can draw peak currents of up to 2 amps. If you tried to pull that kind of juice through a standard microcontroller pin, you'd instantly overwhelm the regulator and crash the whole system. So they smartly wired in a dedicated, perfectly stable 4-volt supply just for the module, ensuring the test conditions were absolutely flawless. This next part is brilliant because it perfectly illustrates how good engineering separates a simple code bug from a hard physical limit. The testing was split into 2 distinct stages, using raw AT commands. Stage 1 is a pure signal check. The system asks the module for its signal quality and its registered network operator. Stage 2 is the actual sending of the text message. But, and this is absolutely key, Stage 2 only runs if Stage 1 actually confirms a connection. By isolating these steps, the team ensured the module could literally see a cell tower before it ever even attempted to send a text. If it failed here, they knew for sure it wasn't a bug in the code. It was a physical network limitation. Which brings us nicely to Section 3, root causes of module failure. So the testing revealed a pretty harsh reality. Depending on 2G in South Africa is far from foolproof. The team physically swapped out SIM cards to test the 2 supported networks. On the MTN network, they discovered severe nighttime dead zones. During the early hours of the morning, like 2 a.m. or 5 a.m., towers actually power down some of their 2G capacity. The raw AT commands just returned 0 signal and no registered operator. They then fell back to the Vodacom network, which generally offered better coverage, but the results showed it was still highly dependent on the exact time of day and the specific location. The main takeaway here? The SIM800L didn't fail because of sloppy code, and it didn't fail because of bad wiring. It failed because of 3 fundamental root causes. Number 1, signal availability. The module was working perfectly, scanning away, but physically unable to find a cell tower to connect to. Number 2, power sensitivity. Even with good wiring, those massive 2-amp transmit spikes demand absolute power stability, which is really hard to guarantee in a cheap consumer setup. And number 3, running costs. Every single SMS requires prepaid airtime, which taxed on an ongoing operating cost to a project that's supposed to be budget-friendly. Plus, 2G infrastructure is shrinking globally, so relying on it for a safety-critical system is just a losing bet. Let's pivot now to Section 4, evaluating reliable alternative options. Faced with those issues, the team had to weigh their options. They had to balance internet dependency against reliability, cost, and development complexity. They looked at a local ESP32 dashboard, which is totally free and requires no internet at all. They looked at back-end API alerts to trigger WhatsApp or email notifications. Those are free but need stable Wi-Fi.
They obviously had the unreliable SIM800L we just talked about, and they looked at more modern 4G options, a dedicated LTE module, which is reliable but requires really complex new firmware, and an LTE pocket router, which handles all the cellular complexity externally and just gives the ESP32 a simple Wi-Fi hotspot. This matrix proved that shifting away from raw 2G text messages opened up way better possibilities.
When you look at broader hardware buying guides for the IoT market, the reality hits you pretty quickly. Right down there at rank number 5 is our SIM800L. Sure, it's incredibly cheap, ranging from just 80 to 200 Rand, but look at the advice column. It is explicitly rated as an SMS backup only. The engineering community itself basically recognizes that this module should never be your primary line of defense. The more reliable options, like the A-series or SIM7600 modules at the top of the list, are significantly more expensive, pushing well over 1,000 Rand, which completely breaks the budget constraint of the whole project.
So this brings us to a really fascinating compromise for academic testing and demonstrations. If the system needs internet for those modern API alerts, how do you provide it without writing super complex new cellular code? The answer was an external LTE pocket router. It's vastly superior for a final year project demo because it completely removes the wiring complexity and all that AT command debugging. The ESP32 code gets to run completely unchanged using standard IoT messaging systems, like Wi-Fi MQTT protocols. The router handles the cellular connection, the ESP32 handles the leak detection, and everything remains perfectly stable.
And finally, let's look at Section 5, the final system architecture.
The team ultimately established a rock-solid primary alert path. The system uses a local ESP32 dashboard paired with immediate physical responses, a loud buzzer, a flashing LED, and an automatic physical valve shutoff. This is the dependable path that guarantees safety first. Think about it. This setup actually stops the leak from flooding the house, regardless of whether a cell tower is powered down, regardless of whether you have Wi-Fi, and regardless of whether your prepaid airtime has run out. It operates 100% independently of the outside world.
Then, on top of that ironclad physical safety layer, they added an optional convenience layer. This includes back-end API alerts for WhatsApp and email that only trigger when the ESP32 is connected to a 2.4 GHz Wi-Fi network or an LTE hotspot. Meanwhile, the unreliable SIM800L 2G code wasn't just completely deleted, it was disabled by default and officially documented as a failed but highly educational test. By structuring the system this way, the API notifications serve as a modern, internet-dependent bonus rather than the core life-saving mechanism. I'm going to leave you with this provocative thought on hardware engineering. If a system requires an external cellular connection, something completely outside of your control, to stop a flooding house, is it really a safety device at all? True safety has to be local. True safety has to be independent. I hope this explainer showed you exactly why real-world physical testing and occasionally failing is the absolute only way to build truly resilient systems. Thanks so much for joining me, and keep questioning hardware around you.